Okay, I think you'll be able to hear me now. So towards the end of our morning lecture, we wrote down the Bayes theorem and introduced the concept of likelihood. So let's recall some of the fundamental theorems that we wrote. The posterior probability of observing a signal h given the data. This was the quantity of interest to us. Remember, these are all vectors. So P of h given x, this is the posterior probability, was related to the likelihood of getting that data when the signal is present, multiplied by the prior probability of the signal itself, divided by a quantity that we call evidence, which is the probability of getting the data itself in the first place. What we did was to write this expression in a manner that separates out the dependence on x and dependence on the prior probabilities separately, and show that this was equal to lambda divided by P of 0 divided by P of h less lambda itself. So that's the final result that we wrote down, where lambda was called the likelihood. This is the likelihood ratio, as opposed to this, which is called the likelihood function. This is called likelihood ratio, and it was equal to probability of obtaining the data given the signal divided by probability of obtaining the same data given the noise. That's what is of most importance to us, this likelihood ratio. That is the one that contains data, the other quantities don't, or rather P of 0 and P of h are our prior information. Before we go on to actually work out what this is, I want to take an example, a simple example, and illustrate how sometimes preconceived notions could fool us to thinking that we have detected something or we have found drug for a new disease, even though the posterior probability of that happening might actually be pretty low. And instead of, the normal thing is to take an example from medicine, but I will actually take the example directly from gravitational wave data analysis itself, and illustrate the power of the Bayes theorem. This is worked out in our Living Reviews in Relativity article, which I have posted in the Dropbox. So what we have in mind is the following, if I can find it. Yes. And in fact, it is cast in a slightly different language, so I'm going to write this down here. Let's suppose T is a test. Let T be a test that is performed on a data set to see whether a signal is present or not. And what we are asking is, what is the probability that a signal S is contained given that the test is true? Well, that is from Bayes' theorem. The probability that the test is true given the signal multiplied by the prior probability that we have the signal divided by the probability of getting true signal for all reasons. True, it's a test. The test can be positive, right? It could be even tossing of a coin. You see the data and you toss a coin and you can decide, depending on heads or tails, whether or not it contains a signal. There's nothing wrong with it. That's one of the analysis that you could do. Let's suppose the probability that your test is true given that there is signal is 95%. Even if you're using a coin to toss to test if the data is true, it actually turns out that every time there is a head, or at least 95% of the time, when it had, let's say the signal was present, or when the signal was present, the test gave you heads. So the effectiveness of the test when the signal is present is 0.95. I really need this in order to write down the numbers. The probability, however, that the signal occurs is very low. It's only 1 in or 10 in a million. It's 10 to the minus 5 or 10 in a million. Most of the times, you get some piece of data, it doesn't contain any signal. Moreover, the probability that the signal, the test becomes true when it is a pure instance of noise, that is, no signal is contained, is actually pretty low. It's 0.01. And remember, these two don't add up. This is the point I was making. These don't necessarily add up. It's 1%. In fact, you can make this test so good, it could be 10 to the minus 3 or 4. It doesn't matter. They don't need to add up. Okay? Yeah?
What factors does that depend probability of test given the signal?
Sorry?
What factors does that depend?
Which one? S, P of S, or this one? That depends on the power of the test. If you are going to do match filtering and apply chi-square test, that might be 0.95. If you don't apply chi-square test, it may be only 0.8. Okay? Or if you don't do match filtering at all, you just look at some threshold crossing, it may be 0.5 or 0.3 or point. So that really depends on the test or the data analysis method that are applied.
That's the efficiency of the test.
Huh?
Is that the efficiency of the test?
It's the power of the test, as it is called in signal analysis literature, is the power of the test. Okay? These two don't, I mean, there's no reason to add up. This t given s and t given 0 are not, complement of one another. They're not. Because this can be, p of t can be also generated by other things. Okay. Yes.
And 0.01 means that if there is no signal, only 1% of the time the test fails.
No. Test will be true. It says the signal is present. It's a false alarm. It's a false alarm. Okay? 1% of the time, when there is no signal, this signal present, the test is positive. It says there is a signal present. That, okay? So this what we would call false alarm. There is a lot of uncertainty in what, sorry?
P of S.
P of S, yes. There is a lot of uncertainty in certainly this, that's the prior. And this was the most controversial thing in Bayesian data analysis, and still remains to be so, and correctly so, because it depends on what you choose for PFS and what parameterization you use for PFS. Simply saying, I don't know what PFS is, I'm going to choose it to be flat across the parameter space. I'm saying PFS, but that might depend on some parameters, lambda, alpha. If I say all of them are equivalent, depends on which parameter you choose. If you change the parameterization, what was uniform once is not uniform anymore. So Bayesian analysis initially had difficulties because people were not ready to accept this prior information, that we should not be biased by priors. If you have Sivia's book on Bayesian analysis, it's a beautiful book, short, I would recommend you to read it. He gives you an example of how the posterior changes as a function of observation. If your prior is so biased, it's very flat. Let's take an example. I want to make measurement of masses of binary systems. And it turns out that all binaries have masses 30 solar mass and 28 solar mass, all of them. There's no exception, it's peaked. But then if you assume that the prior distribution is actually flat for the component masses, it takes many, many experiments before you actually begin to see the distribution. So if you start off with probability of m as a function of m to be flat, after one experiment, this might change a little bit. In fact, it doesn't change at all. After one experiment, it might, you might observe something here at this point. After one thing, how can you be even certain this has given you any information? It might change a little bit, something like that. After two, well, you may observe something here. It will still be very small. It requires a large number of experiments before, well, sorry, the second one cannot be there, right? The second one is also there. It might be slightly peaked, but it will still be broad because that was your prior. For the second experiment, this becomes the prior, but after the second observation, this becomes the prior, and so on, and it's only after a long time you will see that there is a peak here. So prior really influences what our posterior is very strongly. And assuming uniform prior does not mean somehow our results are going to be okay. All right, so in addition to that, what else do I need? I also need what's the probability of not getting any signal at all, P of 0, that should be 1 minus 10 to the minus 5. That we know already. Is that correct? So we can now write down let's suppose in a particular experiment, let's suppose you conduct an experiment in the sense you take data as a particular data set. Your answer turns out to be true. What is the probability that you actually have a signal in it. We can plug in the various numbers and calculate the posterior. The only quantity that is not known now is that. Let's do this on the side here. Probability of S given T. We know T of S is 0.95 multiplied by P of S was 10 to the minus 5 divided by P of T, which is P of T given S times P of S plus P of T given 0 times P of 0. We know all those things. So let's compute 0.95. This is really 10 to the minus 5 divided by P of T given S. That's the same as that term. So it is 10 to the minus 5 plus this is almost 1. P of T given 0 is 0.01. I'm sorry, 10 to the minus 2 multiplied by P of 0, which is 1. So this term dominates here compared to that term. So I get 10 to the minus 3. So the probability of obtaining, the probability that the data contains the signal is actually pretty low. It's only 1 in 1,000, even though our test is very good. The test is fantastic. I might claim that I have a very good test in detecting signals, both in terms of this as well as here. Look at that, right? I have only 1% false alarm probability and 95% true alarm probability. But even then, when I see that the test becomes positive, the probability that it contains the signal is only 1 in 1,000. Why did that happen? It's because of this. There is a very low prior probability that our data contains a signal. We ignore it. The chance of occurring a particular disease might be very rare. Your test might be extremely good. But even so, unless the false alarm rate can be controlled, this is the culprit, because that was not small enough. If this was small, very small, in fact, 10 to the minus 10 or something, this could have been almost 1. But it was not. That's the reason why having a good test is not good enough, but you also have to have something, low false alarm probability. That is something that LIGO achieves by having a very high threshold for detection. And we will do a simple exercise illustrating that later. All right, this is the quantity that we want to compute. And remembering that x and h are both vectors. At the moment, I have written as though they are time domain quantities. It is useful to write them in terms of frequency domain. It's no big deal whether or not we work in frequency domain or time domain. So I'm just going to write that as P of x given h to denote that they are frequency domain quantities, but still vectors, but frequency domain quantities, okay? Whether I work in the frequency Fourier domain or time domain, it doesn't matter. Next, it turns out that it is sufficient for us to just compute the probability of x given 0 because, or in the absence of noise, because I can work out the other probability by saying this is nothing but P of x minus h given 0, as you can see. Because of our fundamental assumption, remember, we assume the data can be either just noise if signal is absent, or n plus h if signal is present. But this second statement is the same as saying x minus h contains no sigma. Therefore, when we compute these probabilities, it's enough to just compute that. The expression for this can be obtained by simply substituting x minus h here. Okay? So let's just compute P of x. What is P of x? 0. Now, we made the assumption that noise n is Gaussian with 0 mean. And some sigma. Therefore, the Fourier transform of this at every frequency Fi, the notation is not good. Let me just erase this, write it properly. The noise at frequency Fi, which I'm going to denote as Ni, is also a Gaussian random variable for reasons I mentioned. Fourier transforms are simply linear functions of the noise multiplying by plane waves. Therefore, Ni are also normally distributed, also obey or normal, just call it normal, with some variance, which I'm going to call sigma I. So these sigma i's are not the same as that sigma here. I probably could use the capital sigma, maybe, just to have the same analogy. Here, at noise at every instance has the same sigma, but here at different frequencies, because it's not white noise, it has different sigma i's, and that's what it is. In fact, this is nothing but SHFF, that SNFF that we have come across. That is nothing but the variance of noise. Okay, so P of x in the absence of noise, therefore, for a single data point, that means at a single frequency xi, is a Gaussian distribution, 1 over square root of pi capital sigma I e to the minus xi star divided by 2 sigma I. Okay? But we want to ask the question, what is the probability of getting a sequence x, the vector x? That would be the product of I equal to 1 to n of P of xi given 0. Okay? So we need to just compute this. What happens here is because of the exponential, in the exponential, the product will give you sum. In the denominator here, you have sigma I. There will be product of sigma i's. It will be sigma 1 to sigma n. But noise at different frequencies is uncorrelated. The product of that is nothing but the determinant of the covariance matrix, which is the inverse of the Fisher information matrix. So that is just determinant of the covariance matrix, C. So P of x given 0 then, in the absence of the signal, will be 1 over 2 pi to the n by 2, 1 by determinant of, I can just write it as c to the, not just, this is determinant of Cij, which I will call c, and here it will be c to the square root of c, and in the exponential, I have a sum which is minus exponential minus sum over I xi star to sigma I equal to 1 to n. Now you can see this is nothing but the scalar product of the data with itself. Right? That's what we introduced yesterday in the form of integrals, but when you convert them to sums, this is nothing but the scalar product, apart from this factor of 2, which I will pull out. So what we have then is that P of x in the absence of signal is some constant which I really don't care about, but proportional to e to the minus 1/2 of x with x. Okay? The reason why I don't care about is because we really want only the likelihood ratio. The whole posterior probability has been expressed in terms of that. Therefore, lambda, remember P of x minus h can be used now, x minus h. I'm not writing arrows before, so let me not confuse by writing them down. Delete this. And this is what I meant by saying I don't need to recompute it, just substitute for x minus h here. It's e to the minus 1/2 x minus h, comma x minus h. This derivation, which appears for the first time in very good detail in Sam Finn's book, he actually works it out in the time domain. He doesn't do this transition. And so the calculation is horrendously difficult, 4 or 5 integrals maybe, but this is much simpler if you do it in the Fourier domain. Okay? So now we have the lambda, the likelihood function. It's the ratio of those two. That's the reason why I need not worry about this, whatever is there here. It's the same thing that appears. You might wonder what's happening to this sigma in the presence of noise. That doesn't change. It is the same sigma. Unless, of course, we have a signal-dominated data set, in which case none of this is going to work anyway. So lambda then will be e to the minus 1/2 x minus h divided by e to the minus 1/2 x comma x. So let's simplify this. It turns out that I can just, we can do this calculation here. X minus h comma x minus h is nothing but x. It's purely, it's completely distributive. The scalar product is fully distributive. So I can just write this as minus 2 x comma h plus h comma h. So this x comma x will cancel with this, and the other two terms will remain, giving us the desired answer, lambda equals e to the minus 1/2 half goes away, I guess. No, I can keep it like that. H comma H. Minus 2 x comma H. Okay, that's the likelihood, and this is what we really compute in our gravitational wave data analysis. When you, after we have made a detection, the detection problem, involves computing these, this quantity here, and this is like a normalization. We take it out. Let's suppose that x is actually equal to h, then the likelihood that we have is e to the minus 2 and 2 will cancel, giving us, so if you have a very strong signal, we can neglect this x can be h itself, right? If SNR is very large, or the signal strength is high, then x is h itself. I'm just trying to compute what is the best you can do for lambda. Then lambda is e to the minus half. There is 2 here and 1, so it is just minus half h comma h, but this h comma h is rho square, signal to noise ratio square, so you have e to the minus rho square upon 2. Oh, it should be plus, I guess, not minus. So the likelihood grows exponentially when you start having, signals of greater and greater strength. And not just like rho, not like just like e to the rho square. So there is a tremendous difference between a signal of strength 10 and 12. They're not same. You might think the signal to noise ratio rho square, or rho, is only 10 and 12, or 10 and 11 even. You might think that there is not much difference between those two, but there is. And this is beautifully brought about by our analysis. And I will show you what that is after talking about how we compute false alarm probability. And it's all because of this. The likelihood function is a very steep function of signal to noise ratio. Let's write that down. The likelihood is a very steep function of SNR rho.
Noise being Gaussian, right?
Yeah, but it is very well reflected even, our data analysis eventually is so good. It's glitchy and not, but eventually it follows the Gaussian. The final process. You may remember the Babak et al. Paper. Were you part of that? I don't know whether you were. That's a CBC pipeline paper. I have included that. You can go through the CBC pipeline paper. It will tell you how we make the data look Gaussian in the end. In the beginning, it's completely crap. I'll talk about that once I talk about background, because I do want to talk about background estimation. Okay, that's about the detection problem. Let's see if I have anything else to add to this. The question? Okay. Say it again.
I had a related question regarding the prior issue.
Yes.
So in general, suppose if you don't know anything about any of the parameters of some, how do you go with using that certain, like suppose let's say component mass, if you use that prior and component masses, then probably the analysis is not biased or biased for the value, the posterior distribution of component mass, but it's biased for mass ratio or charge.
It is true with all choices of priors. No matter what you do, I might be interested in chirp times, because I'm the one who invented, and I would like to know about the distribution of chirp times, and it will be biased because it's a nonlinear function of masses. So you can't really satisfy anyone until the likelihood really becomes strong. How can it become strong? Then actually it doesn't matter whether you use Bayesian analysis or frequentist analysis. Actually, that's the point that I used to make, although Bayesian analysis is good because it finally led to some very powerful techniques for marginalization and computing the evidence. That's what led to things like nested sampling, many variations of MCMC. Basically, they are the ones that allowed us. But the prior thing is not going to go away. I can't give you a recipe for finding good priors, apart from those times where it is already established. Okay? But you can see how our one detection has thrown the entire astrophysics community in disarray, because at least 70–80% of the astrophysics community believed you can't form black holes with masses larger than about 15 or 20 solar masses by normal stellar processes. But that changed with one observation. So how do we put priors, right? I mean, if you had put priors in our analysis, actual analysis, that the first discovery cannot be accepted at all. The second one probably can be, but the first discovery completely throws out. So that's why we deal with priors which are flat in some reasonably good parameters. And the other one is so-called Jeffreys prior, which is supposed to be unbiased, but that works only with certain parameters such as distances, but not always. It doesn't give you unbiased things all the time.
Is there a framework for doing a structured prior sensitivity analysis?
What sensitivity, sorry? Prior sensitivity?
Prior sensitivity analysis. In the sense that analyzing the sensitivity of the result
Right.
to the prior that we have put.
We can, yeah, that's what is done, for instance, in the calculation of rates. You assume that the masses are distributed flat across the whole thing, or they are just at that one point, or that there is some power law. You get different answers. This is precisely the point, that one can do those analyses, and probably the best we can do at this time when we have not established a particular physical parameter, to take different values and say, hey, this is the result that you get based on different priors. And you can marginalize over all those priors as well. I mean, Bayesian analysis is flexible enough that you can say, I'm going to marginalize and give you a distribution that is wide enough. When you start doing this, you extract little and little, but that's what the game is all about. Okay? I think that's done currently in the way we do. Not for all the parameters though. We don't do it for every, masses. Yes, we do something, but should we be biased about the sky? I mean, that's one thing which is completely clear, isn't it? I mean, we know that the signal can occur anywhere in the sky, but we can use the antenna pattern to then say, what is the probability that I observe in one part of the sky? It will be stupid to say that in the close to the null direction, I have a gravitational wave coming in. So what we do then is, when we estimate the position on the sky, we use the antenna pattern function as priors for our distribution. So for some parameters, it is very easy. For other parameters, it's difficult. Any other questions? Yeah. Sorry?
Explain once more the meaning of the vector
X. The X is nothing but the Fourier transform of the data. X is the Fourier transform of the data.
What's the meaning of the vector?
Oh, vector X.
Yeah.
Oh, okay. Yeah, I didn't write it all the time. It is just the collection. X is nothing but the data set Xi. Similar to, the small X vector was the sample data. This is the sample data, right? It was the n tuple, x1, x2, xn, small n. Whereas this x, xi, is the Fourier transform, the discrete Fourier transform. I didn't introduce it, but assumed this may be okay. Xi e to the minus 2 pi I j divided by n. That I is not a good way. That might be. We need also an I which is square root of minus 1. Okay? That's the Fourier transform. So these xj's are nothing but the Fourier transforms. No. These are the data sample at different times. X1, X2, X3 is the data at different times. I think we did this yesterday. I said xk was x at tk. Okay? Okay, and so xi, this capital Xk, is x at frequency fk. Okay? There is
The x there.
x comma x. Those are all vectors.
I mean the x there. Without the vector.
Oh, these are all vectors, yeah. All these are vectors. At some point I said I'm going to stop writing the vector notation. Okay, sorry. We should not be there anywhere. My notation is that capital X now stands for the vector itself. Okay. Man, you're laughing.
You erased the one place where you see that.
I know. It should have been there everywhere. Yeah, that's good. That's what made him ask the question. So, yeah. Sorry, the notation is very difficult and sometimes can be confusing. That's the advantage of giving PowerPoint-based lectures. You tend to have fewer errors, but this I thought is better. Okay. Completely unrelated to this is the estimation of background. So we talked about the detection problem. We are computing the likelihood. And this is not the most difficult thing in our analysis. What is difficult is really the understanding of what the background noise is. Because you saw in that example that the background noise is the one that screwed up our computation. The only reason why I want to talk about this is that's the one that tells you how beautifully Gaussian our data is. I want to bring up the slides because I want to show you real data and discuss it in that context. Maybe you can bring the slides down. Let me explain how this is done, and then we will look at the results. It will come down there, right? So I'm going to start here. So a critical thing that we need to compute, as I mentioned, is the false alarm rate or false alarm probability, shortened to FAR or FAP. How do we do this? Well, you get triggers from a network of detectors. So let's suppose you have detector 1, D1, detector D2. Each one of that data from each of these detectors is analyzed separately, and you collect triggers. You collect potential events or triggers. We looked at match filtering yesterday. What you do is accumulate events based on setting a certain threshold to the match filter statistic. You accumulate triggers, and these triggers are then compared. Do I get the same trigger in each of the data? So you apply a coincidence test. What it means is that you have a set of triggers coming from one of them, and you ask whether there are triggers that are corresponding in this. So if this is the parameter space, I'm representing here the parameter space, do we have a trigger in the same part of the parameter space corresponding to that? And that is called the coincidence criteria. And this reduces the false alarm rate already. That's one way to reduce. Because in a single detector, the triggers might exceed your threshold, you record them. You have 2 detectors, and then you ask the question, do I see the same triggers in both? If you do, you keep them. That's one way of reducing. And then you can apply these chi-square tests. That can reduce the triggers further and so on. But eventually, you will be left with some small number of coincidences. You are applying a coincidence test, and then you have coincidences or coincident triggers. How do we know that any one of them is a real gravitational wave? We don't, not immediately. We can only assign a certain significance. And how do we do that? So you take triggers from one of the events. Let's suppose this is the time axis. And there was an event here, there was one there, and so on. And you had events in another, triggers in another one. This is D1, this is D2, an event here, and so on. This is real time. Your so-called zero lag experiment produces coincidences that could be potentially true gravitational wave triggers or might be false alarms. We don't know that. Okay, they contain both. So I'm just comparing, right? Here was a coincidence, I put a window around this. Okay, I found a coincidence, but there was no coincidence here, and so on. But this will be done, of course, in the entire parameter space, but the false alarm is computed using only the time domain information. I'll come to that in a minute. So, but the zero lag experiment contained both true gravitational wave events as well as spurious events generated by noise. However, if you now do an experiment where you shift the data from the second experiment, time plus some t naught, then all these events get moved at a certain time, And if T naught is larger than the light travel time between the two detectors, then any coincidence I now find between triggers in the two should contain no gravitational waves, unless gravitational waves travel at not the speed of light, but something else, okay? So by time shifting the data of one of the instruments related to the other, we will be able to get, so time lag experiment contains only noise generated events or false alarms. So this is how we compute the background, and that's shown in our results paper. To me, what I want to impress upon you is really the way the background falls compared to the foreground. I think it went to sleep. Do I do something here to wake it up? Ah, there it is. There. Ah, no, that's not the way. Okay. This is straight from the paper, the PRL paper, the first event. I think I have some laser pointer here. This is the detection statistic rho cap, rho C cap. It is made up of the true signal to noise ratio and the chi-square that we were talking about. Somebody asked me yesterday what that rho cap was. I think I mentioned it is rho cap is a function of rho and the chi-square that we compute. I think it is roughly equal to rho square divided by, no, I don't think I'm going to recall that. All that is important is to remember when rho is large, rho cap and rho are the same. When rho is small, less than something like 12, it is weighted down by chi-square. So it's really when, I've not written down anything there, don't worry. So what's plotted here in black is the false alarm that you get by comparing your original data set with the time shifted one. And you do not just one time shift, but as many as is allowed by the data. Thousands and thousands of them. That allows you to obtain the number of events as a function of detection statistic. This is not a cumulative plot. It is the number of events in each bin as a function of detection statistic. So that's the black curve. And look at how sharply it is falling off as a function of detection statistic. Something that's at the level of 10 and 11, or maybe we can go down something like 9 and 10, or 2.5 orders of magnitude difference in this number of events. The significance grows extremely quickly as a function of the detection threshold. The black one includes the so-called, the event itself while computing the background. And because of that presence of one signal, it actually corrupts or gives you large values of events. It's only 1 in 10 to the 5 events, but it still gives those events because that loud signal was present in the data And it was correlating with random occurrences of events somewhere else in the data. That's the reason for this one. If you remove that event and then recompute the background, you get this purple curve, which at low signal to noise ratios, the presence of the signal does not matter, but at high signal to noise ratios, it does seem to matter. So that's the way we compute the background, but we can make an estimate. We don't need that anymore, we can turn it off. I want to make an estimate of what is the probability of getting a certain signal to noise ratio, and how much signal to noise ratio do we really need to have a high confidence in our detection, and compare it with the empirical method there. Can we just get rid of this? If you tell me what's the button, I can. It must be what power? No, not power on.
Yes.
Oh, just up. Okay. Yeah.
Was the number of time lags allowed by the system, is it? I'm correct?
Is what, sorry?
The y-axis in
Yeah.
the figure was the number of time lags that were...
No. It's the number of events that were found in the time lag data, or in the... Actually, I didn't even tell you anything about the event itself, but maybe we can talk about that tomorrow.
I mean, event meaning you displace the displace with some t0, that is one event? Like,
No, not... So every coincidence above some threshold that we have chosen, it is an event. We have a threshold, right? It's rho c cap that rho cap that we use, which is a function of signal to noise ratio and chi-square. For the moment, just think of it as some detection statistic. It's like the signal to noise ratio. It's weighted down by chi-square. If you choose very low chi-square, there are a large number of events. Let's suppose signal to noise ratio of 3, 2, it's there all the time. Okay? The noise by chance makes your match filter output cross a threshold of 2 easily. That's the calculation we are going to do for Gaussian noise in a minute. Okay? But if you take very high signal to noise ratio, that comes down. It's an exponential fall off, e to the minus rho square, in the presence of no signal. So, in fact, the formula we wrote earlier, this, if there is no signal present, then x will be purely n. This will be n comma h, which is 0. And so the lambda likelihood, this on average 0. If there is no signal present, it doesn't correlate with the data. Then it is e to the minus half h comma h, rho square. Okay? So that's how insignificant it will be. The larger signal to noise ratio you think your data contains, the less likelihood it will be if it does not really contain it. You get the point? It's a mouthful. Suppose you assume that the data contains a signal h, but it doesn't, then the larger the signal to noise ratio you make, because this is the only term that survives when the signal is not present. This will be 0, and it will be minus rho square by 2. I told you that in the presence of the signal, it's e to the rho square by 2. In the absence of the signal, it is the e to the minus rho square by 2. As a result, this is the false alarm rate. So what we were plotting there was how many events am I seeing at different signal to noise ratio ratios as a function of this. That's what we are plotting. It is not. It's the number of events. It's not the number of time slides. So the threshold needed for confident detection, let's try and make a simple computation, our noise P of n dn is, let's say, Gaussian. It's in reality not, but this calculation shows you what kind of signal to noise ratios are required, even in Gaussian noise, to make a firm detection. So that's e to the minus n square upon 2 sigma dn. Now, the probability that the noise alone exceeds some threshold, which I will call eta, probability that n is greater than eta, is the integral from eta to infinity of P of n dn. Now, what should I choose this to be? This is the false alarm rate. It is the probability that noise alone is greater than some threshold eta that I have chosen. Well, that depends on the number of experiments that you do. When we filter the data through templates and look at the output, we are sampling the data at some rate fs. Fs is the sampling rate. Not every one of the data points sampled in the match filter output is independent. However, if I want to be pessimistic about my computation of eta, I can assume that every one of those samples is independent. Let's suppose Fs, that means every sample that comes out is an independent sample. For gravitational wave detectors, this is typically 16 kilohertz. Next, I'm using something like 10 to the 4 templates, or 10 to the 5 templates. The number of templates that I use is n, and there are this many number of samples for every one of those sampled data points. So this would be of order about 10 to the 5. Now, furthermore, I don't expect a gravitational signal any more than 1 per year, but I want my false alarm rate to be less than 1 per 100 years or 1,000,000 years, depending on who you talk to. If you want the so-called gold-plated event, we say we want the FAR to be less than 1 in 1,000,000 years. Okay? So how many data points am I going to have by that time? Well, the number of points then, the probability that n is greater than eta should be less than 1 upon fs into the number of templates. Let me put a subscript there, say number of templates, multiplied by the number of years. I will call this equal to y 10 to the 6. This we can do by yesterday what we talked about. That's how we calculate the number of templates. Yeah. Right? That's about 10 to the 5 for the first observing run. It could be up to 10 to the 6 later on. So what's that roughly? So all this is in this fs is the sampling rate. That's the time. Therefore, the whole thing is dimensionless. So we have 10 to the 4 here, roughly. This is 10 to the 5. And 1,000,000 years is 10 to the 13. So this is of order 10 to the minus 22. The reason why I have been careless with number of years and so on, is that look at how small our false alarm rate has to be. 10 to the minus 22. That's, sorry, false alarm probability is very, very small. So plug this into this equation here, this integral, and ask the question, what should be the value of eta such that this is of order 10 to the minus 22. That's an integral that can be done either by using approximation methods, or if you have a mathematical code, you can plug it in. You ask the question, what value of eta will give me 10 to the minus 22? If it's about 9.5. So this would imply 9.5. A signal to noise ratio of 9.5 is what is required for us to obtain that small false alarm probability.
N is your data samples or your detection statistic?
Sorry?
N is your
It is detection statistic. It's a noise.
So does it follow a Gaussian distribution?
It doesn't. So I'm just saying, if it is Gaussian distribution, this is the result. And for a single detector. Doing multiple detectors should really improve this a lot. We should have required much less because the probability that the same event occurs in both just due to noise is much smaller. Yeah. Oh, you can solve this equation. This is eta equals 9.5. You ask, this is a Gaussian, right? It's a Gaussian integral. So you substitute for P of n to be this, and then you will get 10 to the minus 22. Is that okay? All we are doing is saying integral 1 over root 2 pi. You have to assume sigma equal to 1. Okay? 1 over root 2 pi e to the minus x square upon 2. Eta to infinity equals 10 to the minus 22. Then you get eta is 9.5.
In Gaussian noise, we know the distribution of the Maxwell frequency, right? Some chi-square or something.
Yes.
You can do.
Yeah, you can do a proper calculation. I'm just doing a hand-waving calculation. You're saying that it's a Ricean distribution. Are you talking about the match filter output? That's a Ricean distribution.
Not chi-square?
No. It's because of the square root, and it's the quadrature sum of the two filters, and then there is a square root. It happens to be a Ricean distribution, and then you need to do that. Yeah. More careful calculations have been done, but for classroom illustrative purposes, it tells you that a single detector threshold has to be really large. The reason being that we are demanding on the one hand very low false alarm rate, 1 in million years, and our signal prior signal occurrence is low, one per year. So
number of templates is just 10.
10?
Just suppose that number of templates is just 10.
Yes.
Then it will be of the order means.
We are already in the tail of the Gaussian distribution, and it doesn't matter if you reduce that 10 to the minus 22 to 10 to the minus 15, so you'll still get 8.5 or something like that. Okay, so we are in what is called the tail of distribution. Changing that dramatically doesn't change the threshold so much. In fact, if you make it 10 to the minus 13, I know the answer as well, it's 7.5. Okay, so it's very insensitive to what that is. I don't know what I was saying.
Sir, when you are shifting the data that you are getting with time, but suppose the false alarm that are coming, they will also have some. They also have some time for them, right? So
Yeah.
shifting that, how will you decide? Like they are not just Dirac small. They
Uh,
also have their time.
I think I missed a critical point. So we have, these are the triggers coming out of the detector. They're not true gravitational wave detectors, necessarily.
The triggers
Not
might
necessarily.
have their own time.
Or signals.
Yeah, the triggers that are coming.
Yes.
So even if you shift it, suppose you wanted to shift it with time, then the light will take to go from one detector.
Correct.
But if that the trigger is itself larger than that time, then even shifting that won't be useful.
No, if we have a trigger that lasts for even 10, 15 minutes, what we try to determine is the arrival time, or the time at which the binary in spiral peaks. Let's say, I'm talking about binaries, but it doesn't have to be binaries. It could be a supernova signal. All this analysis, by the way, is for transients. So if you have a supernova going, or whatever it is, we will define a unique time, because that will be represented in all the detectors. So it does not depend on how long the signal lasts. It can last for 15 minutes, but still it's a unique time, which is the time at which the amplitude of the signal will reach peak in the case of binary black holes, for instance. Something unique is what is chosen. Then it does not depend on how long it is. We can actually measure that time in our detectors to fraction of a millisecond, something like 0.2, 0.5 millisecond. We can determine it that well. So we take that into account. When we do the time shift, T0, it's not just light travel time. We actually incorporate it's 10 milliseconds is what the light travel time is. But we actually make our time shifts by more than 100 milliseconds, at least. Okay, yeah. In this particular case, it's just an illustration. I think I should have probably done a correct calculation. Here it is just the noise amplitude. You imagine the match filter output is the signal to noise ratio. It is SNR. It is coming out as a function of time. As Ajit said, it is really not a Gaussian distribution. All I have to do is to change what I put in here. Okay, a Raytheon distribution for it, then I will get an answer, and that can be done. But it's not going to be very different from the 9.5 I got. That's all I'm saying, right? You want to put, why not use the proper distribution, chi-square or Raytheon or whatever it is that is relevant? You could do that. It's not going to change the result too much. I'm just trying to say that we are really in the tail of the distribution, and the signal to noise ratios required are large. The problem is, even though we have coincident detection which must reduce this significantly, it doesn't, because our noise is not Gaussian. And none of this calculation is useful when it is not Gaussian. And this is the reason why we have to improve the data quality. And in the end, it really falls off, as you saw, like a Gaussian. There's a poster or a paper by myself and a student of mine that actually shows that the LIGO data quality cuts that we apply eventually give you data that is as good as Gaussian data, but not in the beginning. So the threshold that we are using in our analysis now is a joint signal to noise ratio of something like 9.5 for the network SNR, not single detector SNR, but network SNR. The network SNR, if you have two detectors, ρ1 giving you signal to noise ratios of ρ1 square and ρ2 square, the total signal to noise ratio is that, and therefore, it adds in quadrature sum, so ρ is ρ1 square plus ρ2 square. So this is what we require to be greater than 9.5 for roughly, okay? It might be slightly larger than this sometimes for a high significance event. I should use the remaining time to go back to parameter estimation and Bayesian theory, unless there are some questions. So our second event had a signal to noise ratio between 13 and 15, depending on how you compute it, and that's what gives us 5 sigma event. And the first event, this is for GW 15, 12, 26, whereas the rho for the first event was roughly 25 for GW 15, 09, 14. This is of order 9.3 for LVT 15, 10, 12, which is only a candidate. It is not claimed to be a high confidence detection, but it is a candidate which you can actually see, not in this paper, but I think if you can see it in this. I won't show you here, but you can actually see it. If you go back in paper, there is a second event which you can identify. Okay, that's all I had to say about, oh, it has come back. I don't need to lower the screen. I might be able to just show you. I killed it. I don't think I'm going to go back to this. It's come back. It's all right, don't worry. Maybe we can take a look at it. I will erase the board and show where the second event is. So you can see it there, right there. So those orange ones that we have are the zero lag events. I said these are the two different backgrounds that we have computed, the black and the purple one. These orange ones are the zero lag search. That's our detection. It has a very high signal to noise ratio, almost 25. Whereas this second event here is not so significant compared to the background. That is that LVT 15, 10, 12. You might wonder whether this is any significance. It has no significance at all.
Yeah, I wanted to ask about
nothing.
because in irregular
No, it has no significance, completely consistent with being that, not even 1 sigma. And if you do a proper, some of us don't like this, I'm not supposed to say this in public, but some of us don't like this so-called bind plot. A cumulative plot is better in depicting some of these things, but in the end, it doesn't matter. You can see it's too close to that. We can't have high significance. Even some of the other events here, right, can be true gravitational wave events. We don't know, that's all. And when we measure the parameters, they don't come out very clean. That's the other thing. Okay, so far we talked about the detection problem, but what about parameter estimation? We did that a little bit when we talked about detection theory, but I'm going to introduce, I have another 10 minutes, introduce to the Bayesian parameter estimation problem, and we will continue with the help of some slides to give you accelerated discourse on what these parameter estimation problem is. Give me a minute. Okay. Parameter estimation, just PE. So as before, let's denote by X the data that we have acquired. And lambda alpha are the parameters that we are interested in measuring. Parameters of a signal. we'd like to measure. H is the model that allows to compute the likelihood. In other words, this is the data analysis method. It could be match filtering, time frequency analysis, or just some kind of a burst trigger analysis, whatever you want. That's the method. H is the method. And I is anything else that I use in inferring the data. So I is all other prior information used. So those are the given. Then the parameter estimation problem asks the question, what is the probability? What's the probability that I measure a parameter lambda alpha given the data set X? I'm going to now use the vector X. The method H and all other information I. That's the posterior probability. And as I said, there's only one theorem, the Bayesian theorem, there's only one. And we just apply that Bayes rule, and it says, well, it's the probability of getting the data set given that it contains signal with parameters lambda alpha and the method H and all other information I are used, multiplied by the prior probability of lambda divided by the evidence. So prior probability. You don't need to put this in here, but it is conventional to include that, so because then it will address a more generic problem. So we have just applied the Bayes theorem to compute the prior probability, the posterior probability of obtaining lambda alpha for the parameters. And we have to be told how to compute this likelihood. This is the likelihood, and the method used is H. And for binary in spiral signal analysis, that's just the match filtering algorithm. And we literally compute simply this scalar product that we have been talking about. And I showed you how the likelihood is computed. That's what is used in here as well. Now, this is the joint probability distribution for a number of different parameters. I have masses, position of the source on the sky, inclination, polarization angle, etc. So oftentimes I'm interested in just one particular parameter, P of lambda 1. Just one parameter, P of lambda 1, given the data and the method and all other information. What do I do? The process is what is called, what is this? You marginalize or integrate the joint probability distribution over all parameters except the lambda 1 that you're interested in. So this would be given by integral d lambda 2 all the way to d lambda n of p of lambda alpha x H and I over the relevant ranges of those. So so it's like, I'm not really interested in all other parameters. I want only for the total mass, what is the distribution, that's what it would be. So this is typically, finally, what you see in our papers. And if you go back to that presentation, I'll probably bring it up in other papers. This is basically what we do. But these integrals, oftentimes are very hard to do. As you can see, this might be very large dimension, 10 or 15 dimensions. And that has to be evaluated over that. And that's where one has to invent new methods, and I'm going to talk about that tomorrow. Markov chain, Monte Carlo, and others. The mean can be computed. It's all the rest of it is what you know already in probability theory. The mean of a particular parameter, let's call it mu, is nothing but the expectation value of that parameter lambda. And that would be simply go from lambda min to lambda max allowed by your parameter, a particular parameter, multiplied by lambda, and then P of lambda alpha given, this is the posterior probability distribution, D lambda. Because what I've done is I've dropped this lambda 1 here in the next step, just to say that's for one parameter. If you want to compute it for a bunch of different parameters, well, just compute the probability distribution for that particular parameter, and then you can work out what the mean is, and that's what we do. Similarly, you may want to quote the variance. The variance, or you may want to quote the standard deviation, which is often quoted in our list of parameter values. You can compute that again from this prior probability distribution. So the variance, sigma square, is nothing but the expectation value of lambda minus mu whole square. And you see, we are really following, the method is generic, but the interpretation of, okay, let me first write it down and come back and say what I wanted to say. So this would be again lambda into lambda max of lambda minus mu whole square, P of, not lambda alpha, just lambda given x, comma h, comma I, and d lambda. That would be the variance. We can not only calculate the mean and the variance of single parameters, but we can actually calculate the whole covariance matrix we talked about, namely sigma ij or Cij as they are denoted. They are, these symbols are used interchangeably. It is the expectation value of lambda I minus mu and lambda j minus mu. That's what expectation value is. Then you have to use the full probability distribution, the entire one, right? This, and marginalize over all the uninteresting parameters plus this one as well when you compute the expectation value. So it would be lambda 1 min to lambda 1 max, lambda 2 min to lambda 2 max, etc., lambda n min to lambda n max of lambda I minus mu I, lambda j minus mu j. times the probability of lambda alpha, or lambda 1 to lambda n if you wish. That's the posterior probability of the whole thing, lambda n, given x, h, and I, and dn lambda. So you can calculate the whole covariance matrix as well, and we do that as well. So one can obtain, once we have this prior probability distribution, this is the likelihood, you can obtain these results. But the most difficult part here is really doing these marginalization or computing this. And that will be the subject of the very first item tomorrow. And then we will see how to apply these results to learn about the universe. That's the most interesting part. Until then, you have to sweat a little bit. But once you have that, once you have this tool, you can apply it to the data to get physics, astrophysics, and cosmology, which is what I think I'm supposed to cover in 1.5 years tomorrow. Sorry, 1.5 hours tomorrow. Okay, any questions?
To Weber's data, one would have been able to reconstruct that he didn't really see anything.
That was kind of what was done. It was a proper Bayesian analysis. No, maybe not. I don't know whether Bernard Schutz and Chris actually did Bayesian analysis. Maybe they didn't. No, you don't need to. The whole data was reanalyzed by Schutz and what is his name? Chris is his first name. They was really very weak. I think many subtleties were forgotten. The careful treatment that we are talking about here was not at all what was done. And you can see the event rate that we are discovering is many orders of magnitude below what he was seeing. If there was anything, we would have detected already in S3 or S4. By that time, we are already beaten those sensitivities. You are asked, yeah, but not even these tools were needed to show that those were all false claims. Okay, let's take a break. 5 minutes.